So in this video, we will talk about the ANOVA test. So I can say that probably a lot of you guys, just like the chi-square test, will be using the ANOVA test as well. Okay, so ANOVA, basically that stands for analysis of variance. It's used a lot in a lot of different disciplines. So that's analysis of variance. And the reason why a lot of students are probably going to be using this is because it compares a numerical variable, quantitative variable, with a categorical variable with many levels. Okay, so very similar to the t-test for independent samples for means. A good example of this would be differences of GPA, which is a numerical variable, among majors. Now, there's a couple things that you really have to be aware of. Here, you really got to check all of these assumptions. Independence, normality, homogeneity of variances, and continuous data. This is a new one, the homogeneity of variances. That basically means, are all the variances the same? And variances is basically the square of the standard deviation. So remember, in the standard deviation, you take a square root. Well, if you don't take a square root, you have something called the variance. So it's basically still a measure of spread. It tells you how far apart the deviations are from each other. Well, the square deviations. And I'll show you how to test for that. Typically, independence, normality, and continuous data is pretty simple, but you'll see that homogeneity of variances is still also very simple. So first, let's start off with how you're going to test this. So if you're looking at differences of GPA among majors, well, you're basically looking at every major and you're trying to figure out all of their GPAs. So here is going to be my null hypothesis and my alternative. So we're going to have mean 1 equals mean 2 equals mean 3 equals so on and so forth. How many means you have. And then HA is going to be mean 1 is not equal to mean 2, is not equal to mean 3, and then so on and so forth. Okay, so this is how you're going to write it. So that means this guy, H0, is telling you the means are all the same across the board on every single major. Okay, so there's no difference in GPA. HA says, no, there is a difference in GPA. At least one major has a difference. Okay, so here you can say that mean 1, mu1, is basically the mean GPA. I don't know, it could be of business majors. Mu2 could possibly be the mean GPA for STEM majors. Mu3 could be the mean GPA for non-STEM, and so on and so forth. So you basically get the idea. And you keep going to how many means you have, or how many levels you have. So the number of levels basically tells you how many mu's you're going to have. So think of the levels. Remember, it's the options, the number of options that you have in your question. So that's going to tell you how many mu's you have. Okay, so in this case, I don't know how many majors we had, but I mean, whatever. Okay, so now what we want to do before we do the test, okay, we want to make sure that our assumptions check. So you might want to have your assumptions ready. Look at independence. Okay, so again, independence, we look at major and we're looking at GPA. Again, because you guys were my sample, my independence assumption may have been violated. So I don't know if I can say that that all of you guys are going to be independent from one another. So, or a humanities major is independent from each business major is dependent from. I mean, I'm not sure, because if you guys were my sample and you are all in the same household, I'm not quite sure if you will, maybe in your household is the same amount of majors. I'm not sure. So it really just depends. So questionable. So I'll put question mark, maybe. I'm not sure. Okay, maybe the randomness is not there. The independence is not there. Normality, we kind of did this before. So the way that you check normality is that you want to do a cute plot, or you want to be able to do a histogram just by looking at it. So since we're looking at GPA, so remember, you can always use a histogram, look at the GPA, Don't group it by anything. Just look at the GPA. Okay, this is what it looks like. Kind of not normal a little bit, but not really. Okay, so, but if you really want to make sure more nicer, look at the QQ plot, look at GPA, and then you can kind of see that these guys are supposed to be along this line, and they're not quite on this line. Some of them are not. I mean, but for the most part, most of them are. So you can say that maybe, yeah, they're kind of, well, not these two. But you can say, yeah, they kind of look like they're kind of in the line. They look a little bit normal. Okay. So you can just say something like that. So normality looks okay. I'm just going to write, okay, it looks fine. I'm going to skip that one for now. Continuous data, GPA clearly is continuous. So we're just going to put a check mark. If it's discrete, remember it's just whole numbers. And if it's not, then you would put an X here. That is not continuous. Now, homogeneity of variances, how are you going to do that? So remember, we're looking at their mean GPA, and we're also looking at across the categorical variables. So homogeneity of variances. So what exactly does that mean? So homogeneity means they have to have the same variances or the same standard deviations. So the way that you do that is the following way. So how do you test for homogeneity of variances? So how, and one way to do it, so homogeneity of variances. There's many different ways that you kind of do this, but the more fancier way is something called the Levine's test. And I'm going to show you how to do it. Okay, so the Levine's test tells you, is basically is testing this. You don't need to write this down. You just need to kind of know it. It basically, the variance has a symbol like sigma, but it's squared. So basically what it's doing is that it's looking at all of these individual variances and seeing if they're equal or not equal to. So that's basically what it's doing. Okay, and in this case, what we want, because we want the homogeneity of variances, we want all the variances to be the same, you want the null to be correct. So with the Levine's test, you want a high p-value. You want the p-value to be as high as possible. Okay, this is the only time that we really want the p-value to be high with the Levine's test. Just the Levine's test, not the ANOVA test. The Levine's test has to be a high p-value. If it's high p-value, that means that all the variances are basically the same. If it's a low p-value, that means that they're not the same. Okay, and that homogeneity of variances was violated. Okay, so now how are we going to do that? So we checked continuous data, we checked normality, we checked independence. Now what we got to do is check the homogeneity of variances. So let's go to Statcrunch. Let's click on Stat. We're going to go all the way down to ANOVA and click on one way. Now here, don't click on that. I don't think any of your variables are going to be like this. So let's click on this one on values in a single column. Let's click on responses. That's going to be your GPA. And then let's click on factors. In that case, what's major? Okay. Then before you continue, you're going to click on test of homogeneity. It's really, really smart right here. And then you have two options. You have Levine's test, which is what you want. And then you have another one, which you're not going to click on that one. Okay, click Levine's test. Okay. And then you're going to press compute. Okay. And then you have a lot of stuff. So basically, here you're going to have all of the majors and all of the GPAs. So you can visually kind of see that, I don't know, there's not a lot of difference in the GPAs among the majors. Okay, seems like everyone's kind of like the same. Maybe not this guy, probably just by a little bit. Okay, then you can kind of visually see what the standard deviations look like. So with the exception of maybe the first one, because you kind of have you only have a small samples, but with the exception of the first one, all of the standard deviations kind of look the same. Okay. All right, so now this is what you want, the ANOVA table, okay, the p-value. Okay, now before you go to the p-value, we got to make sure that that indeed the standard deviations or the variances are all the same. So here's Levine's test, okay? You see that the p-value is a little high, 0.37, 37%. So the p-value is high, which is good. In this case, we want the p-value to be high, which basically confirms the fact that the standard deviations or the variances are essentially kind of all the same. Okay, we can assume that. So now, because of that, now we can go to our ANOVA table. So that means that our homogeneity of variances checked it. Okay, so it's all good by Levine's test. Okay, so what you want to do is maybe copy this whole thing into your report, and then you can look at the ANOVA table and say, oh, our p-value, oh, unfortunately was high. So can we say that there's differences among majors? Probably not. So what you would have, since you have 1, 2, 3, 4, 5, you have 5 different categories. You're going to have mu1, mu2, mu3, mu4, mu5. Tell me what each of them are. So mu1 will be the mean of arts and music, mu2 will be business, mu3 will be humanities, mu4 will be STEM, mu5 will be undeclared. So you make sure that you write all of that out. You write all your HO and your HA. Give me the ANOVA table and give me the Levine's test. Okay, so that's what you want to be able to do. And in addition, you also want to make sure that you test for normality. So give me something that tests for normality. You can give a statement about whether something is if the data is continuous or not, and give a statement about independence. Okay, so this one is much more involved than the other ones, but it's for a good reason.